All of the lectures are being recorded and will be available to you on Courseworks, as will my notes. And so I think, you know, hopefully you guys will have all of the materials you need. I will not have a regular office hour, but I am more than happy to meet with you guys. You know, anybody that really wants to plug into this class and learn something from it is somebody I want to get to know. And so you really should not be shy about asking for my time. And I will not always be able to give it, but I will make a sincere effort, especially if you're trying hard to learn the material. And Ding has a regular office hour from 5 to 6 on Tuesdays, I think. Is that right, Ding? Yeah. And we've structured it that way because homeworks are due on Wednesdays. And so you should be able to meet with him over Zoom that way. Somebody had written to me asking about the possibility of having an in-person component for this class, and I'm not going to do that. I'd have a lot of interest in getting to know you guys. I have zero interest in getting COVID. And I think right now in New York, things are ugly, relatively speaking. And so we're not going to do any kind of in-person stuff. So I'm going to share my screen here and just walk you through some of the resources that we've made available. So here is the student view for what the Courseworks page looks like. In organic chemistry, I have made a course website we'll go take a look at in just a second. I've also added here a link to join Piazza, which I'll talk to you about in just a second. And then I've created these assignments here where you'll be able to download homeworks and upload. I believe we can upload our assignments to them, but it's not quite, they're not quite ready yet. Let's go take a look here at the course website. This is a web page that I maintain separate from Courseworks. And there we go. It has on it the syllabus and the outline and various aspects of the grading and whatnot. This class, I decided to stick with the standard format, and we're going to see how it goes. I don't know what it's going to be like to manage homeworks in this way. And, you know, I think the pace is vigorous for Ding to keep up with, since he's going to handle all of the homework material. But right now, what we've got is a midterm exam and a final exam. And then we've got homeworks that are due every 2 weeks throughout the semester. So there are 6 homework sets that you have to complete in addition to those exams. And the breakdown is basically a third, a third, a third. And then I've left 5% for class participation in Piazza. So Piazza is a chat board. It's a place where you can ask questions and get answers from us and also get answers from your fellow students. And so you could discuss confusions regarding homeworks, for example, or exam answer keys, or whatever. And so we'll go take a look at Piazza here in a few minutes. I used this when I taught general chemistry, and it really worked well. The students liked it. I liked it. I thought it was a great resource. And I would prefer that you use Piazza instead of emailing me. Okay, so this was crucial with a class of 200 students. With a class of 28, it's not as bad, but I would rather you not email me. Okay, if it's something about the class that everybody might benefit from, like I'm not clear on what the readings are. You didn't update the web page with the reading assignment. What's the reading assignment? That's a good thing to remind me and think, oh man, we've got to get on top of this. Or, your lecture today was really unclear. You went over this part and you were sleeping when you did it. And so I need you to clarify what you meant by this or that. And that's, having an answer to that kind of thing on the board means that everybody benefits from it. Okay. It also gives the students a chance to plug in and offer their own perspective on what it means. And what I have found is that students enjoy this. Some of you are overachievers and maybe want to be professors yourselves or whatever, and or just kind-hearted people that care about learning the material and want to help each other. And I think especially right now, given that everybody's kind of siloed in their rooms or labs or wherever you are, this kind of a tool is a great way to have some connection to your classmates. Okay, so we'll go take a look at Piazza here in just a second. It's pretty user-friendly, and we can see whether or not you're using it. We can monitor your usage. And so, normally during class, I would have like a bunch of question and answer sort of back and forth, and I'm going to try and do that over Zoom. But my experience last spring was that everybody sits there quietly and, there's not a lot of interaction. So I would like to fix that using the Piazza for that kind of thing. And I'll make an effort as well during class to get you guys to plug in. Okay, so generally the way that I handle the class participation is give kind of a 1 out of 5 percentage points, and that's enough to sway your grade by a half a grade. If you get a B- by the numbers, it can turn into a C+. And so, I really want you guys to try hard to plug into the class and to interact. Like I say, especially because of where we are. The other thing I will say is that the first half of this class is harder than the second. And if you kind of get behind in the first half, you're in a little bit of trouble going into the second half. I have noticed that people are surprised by the material leading up to the midterm exam, and at the midterm exam, they don't do so well. And so I guess what I will say with respect to people who are struggling to get the work done and struggling for whatever reasons with the material, if I see you making a sincere effort to try and learn and move forward by working with whatever the tools available to you, contacting us, etc., reviewing the exams to understand what you did wrong, coming to me for help. That kind of stuff goes a long way with me. Frankly, I don't care what your grade is. I'm going to curve the grades according to what the university suggests the curve should look like, what the averages are. And that kind of thing. And I'm not afraid to give people D's and C's, and I failed a few people over the years. And I don't care that much about your letter grade. I do care whether or not you're excited about the material and whether or not you are interested in learning the material. Okay, so um, if you display that to me, a sincere interest and effort, that does wonders to influence my feelings about you and whether I'm going to give you the benefit of the doubt at grade time. Okay, so if you're really concerned with your grade, then the best thing you can do to influence me positively is to make it clear that you're excited about the material to the extent that you are. Okay. Um, so, despite all of that, there is some sort of strictness with respect to the homework policy. You need to turn homeworks in on time, and if you're late, it's 50% off for the first day and 75% off for the second day. And then if it's more than 2 days late, you will not get any credit for the homework. And that's a big deal. With 6 homeworks, you're talking about big changes in your grade if you don't turn in homework. Okay, so you're not going to do very well if you're not on time with the assignments. The midterm exam is going to be given in class on February 25th. I am still debating as to whether I will give you something that you can take home and do overnight. I think probably what we'll do is just have an in-class session where everybody logs into Zoom and we do the exams. I think my opinion is that if you want to cheat in school or in life, that has some short-term advantages and some long-term disadvantages. And you sort of make the bed you sleep in. And so, I don't like the idea of having to police people for academic dishonesty. And I think especially in this situation, it's very hard to do that. And it's a very difficult time anyway. And so what I'll say is that I do not want you to use resources outside of class to do your exams. And if you're caught doing something like that, then I don't know how that would happen. But if you were to be caught doing something like that, then I'm obligated to turn to the university and say, this person is being dishonest in whatever way. Okay, so with respect to homeworks, however, I would like it if you guys work together, if there was a way to do that. If you're out there wondering, how am I going to meet people to do my homework with? Let's find a way to pair people up. Okay, I think actually that Piazza has a tool for formulating teams. If you want separately just to say to me, look, I'm looking for somebody to do my homework with, I can try and pair you up with other people in the class so you can meet and discuss. I think some of this stuff is much better learned in small teams. And so it'd be great if you could work together on homeworks. The one caveat I'll say is that, you really should be able to work the problem on your own. I mean, if you're just getting together with other people to write down the answers, it's, not a great way to learn. And so, that's up to you to take advantage of that appropriately. Final exam is going to be comprehensive for the whole semester, which will make sense. And I don't know if it's going to be in an exam week or during the class period. Probably it will be during an exam week. So how many of you are in another country? Can you raise your hand, please, using the Zoom function? None. No one's in another country. Okay. So then this time will work for everybody as far as exam. Oh, Barakat is still in Ethiopia for another 2 weeks.
Yes.
Okay, so Yeah, so then this time is a good time for us to be doing the exams in class and all of that kind of thing. All right. So let's see here. Well, I'll return to the textbook, but the textbook is Miesler and Tarr, Inorganic Chemistry. There are multiple different versions. I have them all. I have, well, at least the 4th, 5th, and 3rd editions here. I think I used the 2nd edition when I was a student. And I have to get the readings updated on the course website. And I will take the time to go figure out what the readings are in each of the editions. So if you decide you want to buy an earlier edition, it's fine. The relevant material, I believe, is in all of them. So that might help save you some money if you're buying a used version of an old textbook, if that's a concern. It's fairly expensive, you know, $250 for a brand new version of the most recent edition. But it is a nice book, and the reading in there is worthwhile. You know, most of what I'm going to teach in lecture is what you really need to know to do the exams and that kind of thing. The reading is supplemental, but it's well done and it's worth your time, I think, to really get a lot out of the class. Okay, so over here on the left-hand side, you know, there's this blue button, Piazza Sign Up. This is a place where you can register to be part of the class Piazza page and participate in discussions. So your first task is to go in there and register. So that means going to find the website, which you can do via CourseWorks, or if you want, you can just write down as g4071.owen.chem.columbia.edu. So go in there, plug in, and go join the Piazza page or follow the CourseWorks link. Let me see here if I have it handy. There we go. All right, several of you have already done that. So here's Piazza. Ding did a nice thing for everybody. He went and provided a note and a couple of different links for you to go and start learning the periodic table. Normally today in person, I would be saying next week, we're going to have a quiz where you have to fill out the periodic table entirely. You should know the periodic table. And what you're going to find is that when it comes time to do homeworks, you need to know how many electrons each element has. Okay. You know, you just got to buckle down and do this once. And so otherwise you're going to be slow. You're going to have a hard time following the lecture. And you're going to have a difficult time with exams and stuff like that, unless you use a periodic table, which you're not supposed to. I want you to do the exam problems without a periodic table in front of you. Okay, so go and learn the periodic table and use the links that Ding has provided. Go check into Piazza and go find this thing. And you know, I think what I would like is for all of you to vote down here as to which of these tools you like the best. So your other assignment related to Piazza is to go down here and start a follow-up discussion and respond telling me which one you like, okay? Or maybe you know of another one for some reason that you want to share. But let's just start getting some discussion going here, just for the heck of it, to show that you're using Piazza and that you know what it's about. There's also a bunch of homework assignment folders here. When you make a post, you can go and add it. So like, let's say I'm going to click here, start a new post. Now I'm going to put it in folder homework 1 here. Where is it? Dear Professor Owen, I am waiting for it to be posted. When can I? And then you can decide whether you want this to appear on the course main page, although maybe you don't have this option since you are a student. Yeah, you probably won't see all of those things, but you know, you can post the note. And then in the homework one folder, one of the things you'll see, which will sit at the top of the discussions, they'll sort of go down as more are filled in above them, is this thing. And I can go on and give it a good note, vote, say, I think this is a good post, making sure you want to read it. I can edit it, and I can follow up with more discussion. You could answer it, for example. Yeah, favorites, etc. So there's all kinds of stuff there. Okay, so let's see here if I go back. Yeah. Then on the left, you'll see here posts that have appeared. So you can kind of keep track of what people are writing here. And so, you know, if on homework one, you're unclear about what the instructions mean, write that down, let people respond. And Ding and I will keep track of what's going on here. Okay, so please go to Piazza, use it, and we'll, oh yes, I'll show you. I will show you the statistics page here. I can see who is doing stuff in the class. The number of users looks like on the 9th Friday, there are a bunch of people that signed in, checked it out, or maybe it was just Ding and myself, I've forgotten. And I can also see student contributions, so like the number of posts you've read and that kind of thing. Okay, so that's how we're, and also whether or not you've contributed something. So that's how we're going to use this to measure your participation. Last thing I'll say, you know, there's some outline material. Reading assignments will appear here. I may also upload them on Courseworks. Some of the handouts are going to be here. They will be part of the course notes as well. And then I'll provide links to the lecture materials here. And they will also be available on the Courseworks page here. I'm not exactly sure where yet, since I haven't seen a recording, how the recording to the cloud works. But in any case, we'll see how that evolves. Okay, so Baraket, do you have a question, or is your hand still raised from the?
No, it's still raised from the previous.
Okay, thank you. Does anybody want to take a time to ask questions about this kind of stuff? Are there any uncertainties, or you want clarification? Can I also just see by a show of hands how many of you are undergraduates? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so all right, about half. All right, so then I'm gonna oh no, what? Why do I? Let's see here. Oh, there we go. It's like I just did this. There we are. Okay, so you should be looking at a big white screen. Is that what you're seeing? Yeah? All right, so we're going to start with a little periodic table review. And let's see here. Blow this thing up so I can see everybody. So all right, so let's see. Sorry, I'm still kind of getting used to my. So we're going to talk about the Aufbau principle, which is the building up. So in the hydrogen atom, the energy of electrons increases with the principal quantum number. So what is the principal quantum number? Let's take this guy here. So this is a collection of quantum numbers where the number in front is the principal quantum number. This is the angular momentum. This is the magnetic quantum number. Let's see. Let's do that. And this guy is the spin. M sub s. So in a hydrogen atom, the energy is entirely determined by the principal quantum number, not by any of the others. Okay. And so generally speaking, the lowest energy fills first. You start off with 1s, and then you go to 2s and 2p, and then 3s and 3p and 3d, etc. And the s's and the p's in the hydrogen atom are actually the same in energy. They're just, it's all about principal quantum number in front of the in the front there. In many electron atoms, let's see, does that, you see it sliding too, that's good. Okay. So this is in the hydrogen atom. You end up with electron-electron interactions. And those change the energy. Oops. How did I do that? Come back here. That's not, what is it? There we go. So what do I mean by that? There are a lot of different electron-electron interactions. Coulomb interactions, for example, there are negative charges. They talk to each other. There's exchange interaction, and then there's something called the Pauli principle. So the Pauli principle is a pretty important one. Pauli principle says you can't have two electrons with the same quantum numbers. No two electrons. Okay, so let's take a look at silicon. So silicon has two 1s electrons. It has two 2s electrons. It has 6 2p electrons. And then two 3s and two 3p electrons. Okay, and generally people refer to these guys here as core electrons. And these as valence electrons. And so you fill up the energy levels all the way up to the third level where S fills first and then P. And you have no more than 2 electrons in each of those levels because the magnetic or the spin quantum number is either +0.5 or -0.5 in the S orbital, for example. And then the P's have the magnetic spin number, the magnetic quantum number as well as the spin number. Okay, so let's see here. The core electrons are generally thought of as being unreactive. You know, they don't really do much in the way of chemistry, and so people tend to forget about them and only focus on the valence electrons. And the core orbitals generally have the electron configuration of a noble gas. We know that noble gases, of course, are unreactive. They have electron configurations where you fill up an entire principal quantum number. In this case, 1s2, 2s2, 2p6 is the same as neon's electron configuration. And so sometimes people will write out silicon in a slightly different manner. They'll say it has the core of a neon atom followed by those valence electrons. Okay, so you really only care about, sorry, that should be a 3 there. You really only care about the valence electrons, so you just call that core the same as in a noble gas. Okay, so another very important principle in the Aufbau principle is Hunds Rule. This is a favorite of mine. I think I just like the name Hund. Hunds Rule. Hunds Rule tells you something about ways to place electrons in orbitals relating to their magnetic moment, or their spin moment. Hunds Rule requires electrons fill up to maximize the total spin. So we'll see examples of this in just a minute. Electrons. Let's see here. That's not what I want. There's a way to do, yes. Let's try that. Okay, so I'm going to make a little table here. On the left, we're going to have and the number. Okay, so I've got the atom, the number of electrons, the electron arrangement in the p orbitals, the number of unpaired electrons, and finally the multiplicity. Let's see if I can. Oh, look at how fancy is that. Give ourselves a little more room. I could get used to this. All right, and I'll just. Multiplicity. All right, so we're going to take a look at boron, carbon, nitrogen, oxygen, fluorine, and argon. And we're going to do the electron configuration here. 1s2, 2s2, 2p1. And then I'm going to write out the p orbitals since we're really just interested in the p orbitals for today. And this electron configuration would have one electron here in the first p orbital. That's a total of 1 unpaired electrons. That's n equals 1. And the multiplicity would be 2, since it's n plus 1. Multiplicity is n plus 1. And we call that a doublet. Okay, let's do carbon. 1s2, 2s2, 2p2. Put in our 3p orbitals. And now Hunds rule says we put in the electrons like this. Okay, you could, there's a couple of different choices here. You could put the 2 electrons in the same p orbital. You can put them in separate p orbitals with the spins pointing in the same direction, or you could put them in separate p orbitals with the spins pointing in opposite directions. Total number of unpaired electrons here is 2, and that is a triplet. N plus 1 is 3 in this case, so that's a triplet. So let's do nitrogen. I'm going to replace our 1s2, 2s2 here. Sorry, just the 1s2 bit with helium for fun. 2s2, 2p3. And Hunds says we've got to put all the spins in the same direction in separate orbitals. You know, if you wanted to put 2 electrons in the same orbital, they can't have the same spin. That would violate the Pauli principle. If you want to put them in the same orbital with opposite spins, you could do that. But that ignores Hund. Hund says maximum spin, please. So all of the electrons go in separate orbitals for a total of 3 unpaired electrons, or a quartet state. Oxygen, 2s2, 2p4. Now we have 4 electrons in p orbitals. So I'm going to first start by obeying Hund, and I have 1 left to get to 4, and I'm going to stick it in that one. You could put it in any one of those lines if you wanted, but it better have the opposite spin, because you can't put 2 electrons in the same orbital with the same spin. And so now we're back to 2 unpaired electrons, or a triplet state. Let's do this again. Helium 2s2, 2p5. One unpaired electron is a doublet. And then finally, no unpaired electrons is a singlet. Okay? So, Hund says maximize spin if you can. Maximize spin. And, you know, these rules were written for atoms in the gas phase, but they apply more generally. So let's talk about why this is the case, okay? Why is Hund's rule a rule?
Professor, that last one is neon, right?
You are right. Thank you. Okay. Let's see here. So why is Hund's rule Hund's rule? Well, in order to know that, you need to know something about the pairing energy. Okay, so let's just take carbon, for example. There's 2 unpaired electrons spread out in 3 orbitals. And I said you could make them pair opposite like this. In 2 separate orbitals, you could have the spins anti-parallel. Or you could have 2 electrons in the same orbital with the spins anti-parallel. You cannot have 2 electrons in the same orbital with the spins parallel, because that violates the Pauli principle. But you could have that configuration. So what are the rules that, or what are the components of those electron-electron interactions that make Hund correct? Okay, so the pairing energy is an important concept. The pairing energy is the energy it takes to make the spins align. Okay. So there's 2 parts to the pairing energy. Pairing energy is a sum Does anybody know the 2 parts? Nobody? Pairing energy is composed of a Coulomb term, sorry. And the exchange energy. Okay. So generally speaking, this is a energy penalty. And this is a energy benefit. So this exchange energy is lower the energy of the system. Coulombic repulsion raises the energy of the system. Okay, so you know about Coulombic repulsion. 2 negative charges don't like each other. And then there's this thing called the exchange energy. So what is exchange? Exchange energy is something I've never really understood myself. I don't know the reason for it. It's kind of like saying, why does plus like minus? You know, I don't know how to answer that. It's just the case that plus likes minus, right? So exchange energy is another one of these kinds of energies, and it derives, or you can count it, you can identify it by looking at the interaction of electrons with the same spin. Okay, so I would say beneficial with the same spin. And this is basically what makes Hunds rule work. It's one of the reasons. Okay, so if you have electrons like this and like this, they have different energies. Okay, and what people say is that if you have a state like this and you swap the electrons, you do not get a new state. It's the same state. Okay, and that is where the word exchange comes from. And that's just a moniker to help you recognize the situation. It is beneficial to have electrons in the same orientation, not this one. So let's take a look at the three possible ways to fill up the p orbitals of carbon. So we're going to take 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. And in this first example here, what I'm going to do is I'm going to say this is px, py, pz, px, py, pz, px, py, pz. And in the first one, I'm going to put both electrons in the px orbital with opposite spin. In the next one, I'm going to separate those electrons into two different orbitals, but I'm going to keep the spins the same, meaning anti-parallel. And then in a third, I'm going to write them like this. And which one does Hunds rule favor? I like that Rachel pointed. You pointed the wrong direction according to my Zoom screen, but I think that's because Zoom mirrors your video image. Hunds rule favors the one with high spin, right? This guy over here, this is the one that Hund likes. And that's because it is favorable from an exchange energy perspective. It is also favorable from a Coulomb perspective. So which one of these is least favorable from a Coulomb perspective? Think about a carbon atom for a second with 3 p orbitals pointing in x, y, and z. If I have two charges and I put them in side-by-side orbitals, they're going to have one interaction. If I have two charges and put them in the same orbital, they're going to have a much stronger interaction. Okay, so the case where you have two electrons in px over here is unfavorable from a Coulomb repulsion perspective. This gets a lot more interesting in more complicated transition metal complexes, but simply said, put it in the same orbital and you pay a penalty. So there's a Coulombic repulsion here. And which one of these is favored by exchange? The one on the right is favored by exchange. You can take these two electrons and swap them, and you do not get a new state. Okay, if I take the one in the middle and I swap them, the up spin went from X to Y. That's a different state. Okay, so the one on the right is favored by exchange. Let's say disfavored. Okay, and so among these three possible states, you could rank the relative energy of them. This one on the left is going to be the highest in energy, and the one on the right is going to be the lowest in energy. Okay, so this is the Hunds rule preferred state because of Coulomb and exchange. So you're going to do this again in the future. It would be good if you do that. All right. So I'm going to just make a note here. Okay. All right. So another principle that becomes very important in many electron atoms is the idea of shielding, nuclear shielding. Okay. So let's talk nuclear shielding. So in many electron atoms, electrons that are closer to the nucleus shield the charge and shield the electrons that are further away. Okay, so say I'm a carbon atom and I've got a nucleus that's got a 12 plus charge. Well, as I start putting electrons around it, it no longer feels like it has a 12 plus charge from the outside. Okay, and that principle is shielding. And this makes a really big difference in how electrons fill up. It's really a powerful concept. Okay, so this stuff may feel like, you know, really basic, and you did this in Gen Chem, why are we doing this again? Nuclear shielding and what's called effective nuclear charge are really, really useful concepts when predicting behavior. I use them all the time. This is one of my favorite principles. Okay, so let's just do a couple of different, right, and I'll just say as sort of a precursor to that, different orbitals interact differently with the nucleus because they are shaped differently. Okay, so that's where things start to get interesting. All right, so just a few principles for nuclear shielding here. One, as the atomic number goes up, the electrons are drawn toward the nucleus. Oops. And their energies become lower. So a way to think about this is in terms of a reference state, okay? So if you have an electron that's just hanging out in outer space, it's in a vacuum, it's not moving or anything, that's a good reference point. If you bring now a nucleus close to that electron, as the electron sticks to it, its energy goes down. It stabilizes that charge, okay? So the nuclear charge, the attraction of plus and minus, holds that thing and lowers its energy. You have to expend energy to pull the electron and put it back into outer space, okay? So that's your reference, is the energy of an electron in vacuum. And so the magnitude of that nuclear charge is really important because it dictates how much energy you have to expend to pull the electron off. So it turns out that in outer orbitals, so you're filling up your atom, you got a bunch of core electrons now. Shielding causes the energy shielding causes the energy difference between the s, p, and d orbitals with the same principal quantum number. So you probably remember this. You know that in carbon, the p orbitals are higher in energy than the s orbitals. Well, they're higher in energy than the s orbitals because of shielding differences, okay? The s orbitals experience the nuclear charge more than the p orbitals do, and therefore the electrons are held more tightly to the nucleus when they're in an s orbital. All right, so this is all about shielding differences. So let's take a look at some examples here. Let's do titanium and chromium. So titanium, argon, 4s2, 3d2, and chromium is argon, 4s1, 3d5. Okay, so a couple of interesting things here. One, well, would anybody like to comment on what's interesting about these two examples? Or one of them?
Is acting as a bully because the s orbital doesn't have 2 electrons.
Yeah, in the case of chromium, you have an interesting example where you have 1 s electron and 5 electrons in the d orbital. So you didn't fill up the s orbital first. How do you say your name? Emir?
Yeah, or M here. It's like I'm here.
M here. So M here. Why is that? Why do you think that happens?
I'm not sure. Is it because of the pairing of electrons in the d orbital?
Yeah. And how would you say Hund would feel about this?
Because exchange energy favors each of the 5 orbitals in the d orbital to only have 1 electron because they'll all have the same spin.
Yeah, but what does that say about that 4s orbital having 1? You might imagine 4s2, 3d4 could work.
Well, so that one, 4s2 would have Coulombic repulsion, right?
That's right.
So the energy is more in that state, and it would trend towards a state that's more stable with less energy.
That's right, yeah. Yeah, and so by pulling an electron away from the 4s orbital and putting it into one of the d orbitals, you get rid of that Coulombic repulsion and you gain more exchange energy because now you have more unpaired spins within the d orbital manifold.
Okay.
Yeah. So, Mac, you had your hand up a couple of times. Do you want to comment on the other case or on either case?
No, I was kind of going to say the same thing, but not exactly. So I think I had it wrong, but still. But
Okay.
Yeah, no,
Okay. Okay. So the other thing, there's one more aspect of this that I think is worth commenting on. Does anybody else want to say more?
Yeah, I want to say because there are two extra protons, so it actually lowers the 3D orbital so much that the energy benefit can excite it an electron from 4s to 3D instead of, you know, in titanium it doesn't happen because it's lacking two protons, so that the energy gap is not you know, low enough to compensate the benefit.
Yeah, so that's great. The way I would say that, you know, you could imagine one of the, as Brian pointed out, one of the electrons coming from the 4s orbital and going to the 3d orbital, right? Instead, we have 4s2, 3d2. So why do both of these two electrons sit here? Why not do what Hunds said to do? And you have to consider the amount of energy that you pay on going from 4 to 3, right? Because the 4s orbital and the 3d orbital are not the same energy. So when you move an electron from the 4s to the 3d, you have to jump up, and that costs energy. And it turns out in the case of this titanium atom that that energy is larger than the exchange and the Coulomb repulsion, because the S and the D is too far apart. Whereas in chromium, they're closer together. And the exchange energy that you gain is larger. Now, that's a lot in those two examples here. There's one more point about this that I think is worth raising, and that's why are we filling 4s at all? Why not just fill 3D? The 4 is the next energy level, right? It has a principal quantum number higher than 3. So why are we putting electrons in 4s at all? And the reason is that s orbitals interact with the nucleus so strongly that they come down in energy below the Ds. And as Brian points out, in the case of titanium, that 4s orbital is so low that it doesn't even make sense to obey Hund and go to the highest spin multiplicity possible. Okay, and that's a consequence of nuclear shielding. So you get this funny electron configuration here because of the fact that 4s fills early. Whoops. Okay. So it turns out that s orbitals interact with the nucleus more strongly than Ds. And as you're filling up the levels and you're looking at the relative energies of them, in this particular case, the 4s interacts so much more strongly. It's less shielded by the core electrons that it ends up being lower, okay? So 3D is more shielded by 4 electrons, and 4s. Which leads 4s to be lower in energy than 3D. Okay, and then of course there's the chromium example. Chromium is special. The chromium electron configuration half-filled shell, right? The half-filled shell. That's what people usually say when they talk about this example. It's half-filled, so what? Well, it's important because you get a lot of exchange, okay? By taking one electron, let's say we had, for example, 4s2, I'm just gonna write versus 4s2, 3d4. Here you've got 4 unpaired spins sitting in the 3d orbitals that you can make exchange interactions with. Here, you've got 6, right? And if you go through and count all the possible exchange interactions, there are quite a bit more for chromium than there are in this other state. Okay, so half-filled shells are really valuable because they give you lots of exchange, especially when you're talking about Ds and Fs. Okay, so you get this half-filled shell, which is beneficial. Lots of exchange interactions with the half-filled shell. Okay. Let's see here. Okay, one more thing I'll say is that 5s and fills before 4D and 6s before 5D. So you get the same kind of thing, right? And so I'm going to give this a extra here. This is something you got to know. I'm going to ask you this over and over again. You're going to get sick and tired of hearing it. In many electron atoms, S penetrates to the nucleus. Better than P. Yes. Okay, so S penetrates better than P, which penetrates better than D, which penetrates better than F. So, and this is a really important thing. You're going to come back to this many times over. So, this is why four S fills before 3D. All right, so let's take a look at
Professor, sorry.
Yes.
Yeah. So on this note, like I was thinking also about the like in charged states like ions. Like normally you would just lose the electrons that are placed in last, right? But with like the 3D and 4s, like you actually lose the 4s electrons instead of the 3D, right? And I think like the explanation that I was like given in the past was that like in like when in an ion the 3D orbital actually experiences like a stronger nuclear charge, or at least in the ionic state, which is why like the electrons stay in the 3D rather than the 4s. But that isn't the case for the neutral atom, I guess.
So it depends upon what the environment of the ion is. Like what the ligands are that are around it, for example. If you're just talking about an atomic ion, so, you know, no ligand field, then the S's and the D's are not going to change positions. And in fact, it's just going to magnify this effect. But if you have ligands, that can change everything. Okay, so when we, we'll come back to this later when we start making molecular orbital diagrams, and we have to get the orderings right. Okay. So let's take a look at some wave functions. And what are called radial probability distributions. Gotta love that, my gosh. Can't do that on a chalkboard. All right, so let's take a look at a wave function for an s orbital. 1254, oh darn. I guess I'm gonna have to stop. Almost got through today. Okay. Yeah, so I'll just stop there. So that worked out okay. So I'm going to stop sharing. And I'm going to stop recording in just a minute here. And I'll say, I hope this went smoothly for you guys. I'm relatively pleased, although my handwriting is a little messy this way. I hope that everything's working. If you're having some kind of problem or question, or you just want to chat, you can send me a note. I guess with respect to email versus Piazza, like I said, if it's a personal thing, you obviously shouldn't post it on Piazza. Feel free to email me if you need to, just to let me know if there's something with regard to the class, like, oh, I can't see this, your note-taking application isn't working this way or that way. You could put that on Piazza, it's fine. Or if you'd really rather for some reason send it to me, it's okay. But let me know how it's going, and send me a note if you have anything you need to discuss about the term, or you're wondering about the class or what have you. And otherwise, I will see you on Wednesday. All right. Thank you.
Thank you.
Bye, everyone.
Thanks, Professor.
Thank you so much.
Thank you.
Bye, everyone.
Professor?
Thank you.
Yes.
I just wanted to let you know, one of my friends